it's good sportsmanship to not pick up lost golf balls while they're still rolling from Mark Twain. So you don't want to do that. So let's take a look at what we know. Our learning goals in this particular case is we want to be able to describe the motion of an object based on a position versus time graph. Now you've already generated a position versus time graph in the rolling along lab, so that's nothing new. You should be able to calculate the average velocity from a position versus time graph. Now once again, that's something that's been introduced already. You want to be able to distinguish between speed and velocity, distance and displacement, and average and instantaneous velocity. Those are 6 terms that are very, very confusing for people to be able to tell the difference between, so it's important that you pay attention. And next you want to be able to use the equation V average, and usually this average is kind of a subscript right there, equals delta D divided by delta T. So let's take a look at our variables that we investigated. The first one is time. And time is the interval between events. Time is a difficult thing to actually kind of conceptualize other than the fact that you already know what time is and you've dealt with time your entire life. Time is generally measured in this class with a photogate, okay, and a stopwatch. Now a lot of people want to say that the photogate actually measures velocity. It does not. What a photogate does is it actually has it has a laser and it has a receptor that it goes across and it measures that laser. Now when that laser is broken, the timer can start or stop depending on the situation. And when the laser reforms, that's another indication that something has occurred. So you're looking for the amount of time that the laser is broken or the amount of time that the laser is reformed. Now when you look at time, time is almost always considered to be the independent variable. Now the reason why time is the independent variable is you can't change time. Time either passes or it doesn't. You can't say, I'm going to slow time down, time's going to go backwards. You can't do that. So because of that, time is almost always the independent variable. So 2 terms that are very, very confusing for people to understand at certain points. So let's take a look at what they mean. A distance is a scalar. So distance is how far you actually travel. And so like if I take this and I start here and I follow this path and I draw all the way along, I've actually traveled quite a bit of distance. Okay, that's what the distance is. It's how far you actually go. Now displacement on the other hand, if you were to take a look at displacement, displacement is, okay, here I start and here I stop. What's the distance between those 2 points in the quickest way that I can actually get there? So it's the vector representing the change in position. So whenever you see delta D, that actually represents the displacement. Usually distance itself is just represented by D, or sometimes they actually use the term S for distance. So it's really important that you be able to distinguish between these two, even though both are technically lengths and they're both measured in meters, they have very different meanings. Position versus time graph. So in the lab, we determined that velocity can be figured out by taking the slope of a position versus time graph. So we have a position versus time graph, and whenever we find the slope of this particular line, like we did here with 2.5, that slope of the line actually references to what the velocity is, or how many meters per second the object will actually travel. So, determine the average velocity between 3 and 5 seconds. Now this one's really confusing for people. We said that it's the slope. Well, if you were to take a look right here, between 3 and 5 seconds, if you were to find a straight line, it's about as straight as we can make it, the data doesn't actually follow the slope. They're not the same thing. And so we'll talk about what that actually means later, but remember, the average velocity is just the slope between any 2 points. So you can take this point right here, let's change the color so we don't get confused. We can take this point right here and this point right here, and I could technically find this is the average velocity between those 2 points, even though it has nothing to do with the actual data itself. So when we look at the average velocity, all you're doing is looking at the slope between the 2 points here. Well, if you look at the points are 3, 10, and 5, 25. So when we find the slope of them, we do the rise over the run. In other words, we do y2, which is this is y2, so 25 minus 10 over the run, which is 5 minus 3. So if you did that, you would get 15 over 2, or 7.5 meters per second. Now remember, that would be the average velocity. It's not how fast it's actually going at any one particular point, but it's the average velocity through that time interval. You should be able to determine the average velocity based on this graph, remembering that you have to take any 2 points. Remember, any 2 points on a straight line will have the same value. So I don't care if you take this point and this point, or this point and this point. It makes no difference to me. Now remember, when you do this, though, it's generally easier if you take 2 points that are easy to distinguish. For example, this point right here is easy to distinguish because it lies right on a line and right on a line. This point, likewise, is easy to distinguish because it is, well, I guess this point right here is the next easiest one to distinguish because it would be at 1 second and 10. So it's easy just to pick the 2 easiest points that are to read so that you can get an average velocity value. In this one, it says determine the average velocity of the object based on the graph. So once again, we want to pick any 2 points. You should be able to do this entirely on your own and figure out that the velocity of this object is 1 meter per second. Alright, so velocity and speed. So far we've talked about distance and displacement, and so now we want to put those kind of tests. So velocity is how fast you're going. In other words, it's the rate of change in displacement. So it's displacement over time. Whereas speed is distance over time. But that has some real significant factors there that are going to affect us. So that actually means that velocity is a vector while speed is a scalar. Velocity is represented with the variable v, or sometimes, well, just v for now. And speed is generally represented with the value of s. Because of that, the velocity vector has to include direction. And speed does not. No direction. Okay? They have a couple things in common, though. They both have what's called a magnitude. The magnitude represents the number. So they're defined by, oh, I'm going 10 meters per second, or 60 miles per hour. They're both defined by a magnitude. They're both measurements of how fast you're moving. They are both rates. Rates mean they vary with time. Okay, so they have some things in common, but they definitely have things that are different as well. For example, if I start here, let's change the color real quick. If I start here, or right here on the circle, and I go all the way around the circle, okay, and I end up in the same place that I started at, that means that my velocity is 0. But that means that my speed would be equal to whatever the circumference of this particular oval would be divided by the time. So I definitely still have a speed, even though I wouldn't have a velocity. Because my displacement in this case, since I end up in the same place that I start at, my displacement is 0. So very similar, but also very different. Average velocity represents it's kind of an average between how fast you're going for the whole trip. It's not how fast you're going at any one particular point. It's taking the whole trip. How far are you from where you started divided by the time. It does not represent any particular point. So you can't say, oh, well, since it said that the average velocity was 60, I wasn't speeding. You can't do that. Because you could have been going 70 and then going 50. So you can't exactly use average velocity to figure out how fast, or whether or not you should get a ticket. So example B1, it says you wake up late for school one morning and you walk out the door at 8:36 a.m. You should be able to recognize that right there is a time. It says you travel an average of 60 miles per hour for a 24-kilometer trip. If school starts at 8:45, so once again, that's another time. It says, will you be on time? Alright, in this example, we had a 60-mile-an-hour car leaving a house at 8:36 a.m. and traveling 24 kilometers per, and we wanted to know exactly when it's going to get to school to see if it's on time. So the first thing we want to do is we want to do our given information. And our given information that we have here is that we have a displacement. In other words, how far they actually have to travel is 24 kilometers. We know that they are traveling at an average, we can call it V average, of 60 miles per hour. Now that's actually a problem. Miles per hour and kilometers are not in the same unit. In fact, they're not in standard units. So we're going to need to convert both of those values. So the first one that I'm going to convert is I'll go ahead and I'll convert, we'll convert kilometers. You should know that 1 kilometer is 1,000 meters. And that gives you a new value of 24,000 meters. In addition to that, you have 60 miles per hour. You have 1 hour is 3,600 seconds, 60 minutes, 60 seconds, and that 1 mile is 4 laps around the track of each 400 meters, so that's 1,600 miles per hour, or excuse me, 1,600 meters. When you multiply out 60 times 1,600 times 3,600, you get 26.7 meters per second. So now I have my values in the appropriate units. They're both in standard units of meters and meters per second. So that's one thing you've got to watch out for. So now when we look at the find, what are we trying to find here? And you're actually trying to solve for the time. And a lot of people may say, well, wait a second. You're given a time. You have a time of 8:36 a.m. You do, but that's actually just what time you start. Okay, you don't actually know how long the journey is. And so that time is just kind of a reference point for you to add how long the trip takes. So you're not actually trying to use that particular value at this point. So we know that the object is going to be moving at a constant velocity, or at least a constant average velocity. So we know that the formula that we're going to use is going to be V equals delta D over T, or velocity equals displacement over time. If you look, I've got displacement, I've got velocity, and I'm trying to solve for time, so there is no irrelevant information. So now we can say, okay, what's my solution? Well, now we plug our numbers in. We say I have 26.7 equals, the displacement that I had was 34,000 t. So now we need to solve for t. So we take t, we're going to multiply t on both sides, and we're going to cross it out there, and that's going to give me 26.7 t equals 34,000. Now, some people may be saying, well, why didn't you just divide both sides by 34,000? Because that would actually leave 1 over t, and 1 over t is not the same thing as t, because 1 over 2 is not the same thing as 2. So now you have 26.7 t, 34,000. You divide both sides by 26.7. And when you take 26.7, or excuse me, 34, and you divide it by 26.7, you get 1,273 seconds. But you've got to look at it in terms of time, right? How are we going to get this thing to see if we can make it at 8:45? And 8:45 is 9 minutes later. So we don't actually want the answer to be in seconds. We actually want it to be in minutes. So in order to fix this, what we need to do is we need to take it and divide by 60. And when you do that, you realize that the answer is actually 21 minutes is what the trip takes. And for 21 minutes of the trip, you're going to get there at 8:57, which is well after the 8:45. So you are late. Example B2 says a runner completes a 5-kilometer race, and it says in 12 minutes and 38 seconds. What is the average velocity? You remember average velocity, that better be in meters per second right there. So you're going to have to do some conversions right there for meters per second and then minutes to get this thing to work. Finally, you should be able to solve this one entirely on your own. If you're doing conversions and so forth, you should be able to figure out what the answer is fairly easily, and it ends up being something like 12,000 meters. So velocity on a ramp. So when we did this latest experiment, the rolling along experiment, in order to get the ball moving at a velocity, in other words, before it was flat on the floor, we let it roll down a ramp in order to gain speed. So the velocity's here. How did the velocity at the top of the ramp compare to the velocity at the bottom of the ramp? You should have realized that as the ball rolls down the ramp, it actually picks up speed. So the final velocity is actually greater than the initial velocity. It actually starts out much slower, much closer to 0, and it picks up speed as it goes along. So when we take a look at this average velocity, remember the average of anything means you take the data points, add them up, and you divide by the total number of data points. Well, that's what we did right here. We took 2 data points. We took the final spot and the initial spot, and we added them and divided by 2. Well, now you've got this average velocity equation equals displacement over time. Well, this actually kind of rearranges. You can move the t over and leave it in this. This is the more common form. You'll see this right here, and this is generally said to be the first kinematics motion equation. Kinematics motion equation. Now, there's actually going to be 4 of these, and they're going to be pretty important. So you need to be able to use these. We're going to use lots of examples of how to figure these out. So the first example says you have a toy car that moves down the ramp as shown. It says there are 50 centimeters between the gates. The car has a velocity of 14 meters per second when it passes photo gate A, and 18 meters per second when it passes through photo gate B. The photo gates are separated by 50 centimeters. How long will the cars be between the photo gates? So I'm trying to solve for a time. In this example, we had a ball rolling down a ramp that was by 2 photo gates. It said that the velocity at the one photo gate was 14 and the velocity at the other photo gate was 18. So now we want to go ahead and take a look at how we can solve this particular question. So we have a couple of pieces of given information, and our given information includes the fact that we have an initial velocity, and that initial velocity is equal to 14 meters per second. And in addition to that, you have a final velocity, and the final velocity that it gives you is 18 meters per second. And that is when they go between 2 photo gates that are 50 centimeters apart. Now you should recognize the fact that that 50 centimeters is not in a standard unit. So because it's not in a standard unit, you actually have to convert it. So when we convert between centimeters and meters, you can say that there are 100 centimeters in 1 meter, or you can say that the displacement is 0.5 meters. So now we have all our information that we need that's necessary. We've got our displacement, we've got our initial velocity, and our final velocity. So now we can say, okay, what are we looking for? And we're actually trying to solve for the time that it takes to go between these 2 gates. We want to know how long it's going to be there. So we know the principle that's going to be involved here is the fact that the object is accelerating. So there's accelerated motion. Okay, it's no longer a constant velocity. It's no longer a constant 14 the whole time. So because I have an accelerated motion, I need to be able to use the equation, and the equation that I'm going to use is going to be the displacement is equal to 1/2 the initial velocity plus the final velocity times the time. If we look at what we're given and what we're looking for, I'm going to change colors so we can see it a little easier. I've got the time, or I'm trying to solve for the time, the initial velocity I have, the final velocity I have, and the displacement I have. So there is no irrelevant information. So now we can plug in our values. We can say, okay, delta D was 0.5. And it was going to equal 1/2 of the initial velocity, which was 14, plus the final velocity, which was 18, and then times t. So you can break this down step by step. You can take these and you can add them together because they're in the parentheses, and we can do order of operation. So 14 plus 18 is actually going to give us a value of 32. So now you're going to have 1/2 equals, or excuse me, 1/2 times 32 t. You can break it down even further, and you're going to get 0.5 equals 1/2 of 32 is 16. And so you can say, okay, 16t. So now you've broken it down to the point where you can take and divide both sides by 16. When you divide both sides by 16, you get an answer of time is equal to 0.03125 seconds. In this question, it says a car starting from rest, there's your key thing right there, accelerates to 25 meters per second in 60 meters. How long does this take? So you should realize that you have an initial velocity, a final velocity, and a displacement. And you should be able to solve for the time. Now you should be able to solve example C3 on your own. It says the skateboarder starts from rest and moving 10 meters per second in 12 seconds. How far will the skater travel during this time? You should be able to figure out that the answer is 60 meters, and you should be able to justify that answer with all the work that's necessary to get.